Electric field intensity. Electric field intensity due to a uniformly charged spherical shell. Electric field intensity due to a uniformly charged spherical shell. So this is a uniformly charged spherical shell, and positive charge plus Q charge is uniformly distributed over the surface of this spherical shell or hollow sphere. Sigma is the surface charge density of this spherical shell. R is the radius, capital R is the radius of this shell. We consider a point P on the surface. Unit positive charge, that is +1 charge, is placed at the point P, and ds is the small area. ds is the small area at the point P, or ds is the elementary area at the point P on the surface of the spherical shell. We can denote the electric field intensity. We can denote the direction along which electric field intensity, that is vector E, acts. Vector E is the electric field intensity at the point P, and we can denote the area vector, small area vector, which acts also radially outwards. D vector S is the small area vector which acts radially outwards. Similarly, electric field intensity at the point P, that is vector E, also acts radially outwards. This is uniformly charged spherical shell, and also we can assume that S is the Gaussian surface, spherical Gaussian surface. This is the spherical shell, and which is also which can be assumed as the Gaussian surface. This is the charged spherical shell and spherical Gaussian surface, and this spherical shell is assumed as Gaussian surface. To find the electric field intensity, at the point P on the surface of a uniformly charged spherical shell, of radius capital R, a spherical shell, a spherical Gaussian surface is of same radius capital R, is assumed or is imagined. A spherical Gaussian surface is of same radius capital R is assumed on it or on the spherical shell. And here ds is the elementary area, or ds is the small area at the point P on the surface of the spherical shell. ds is the small area on the spherical Gaussian surface at the point P. ds is the small area on the spherical Gaussian surface at the point P, and vector ds acts radially outwards. That means this area vector ds acts radially outwards for the point P on the surface, of the uniformly charged spherical shell. The shell behaves as if the entire charge, that is plus Q charge, the entire charge plus Q on the surface of the spherical shell. The shell behaves as if the entire charge plus Q on it were concentrated. The entire charge plus Q on it were concentrated at its center O. Now we can assume that though plus Q charge is uniformly distributed over the surface of this spherical shell, it is assumed that this plus q charge is concentrated, and this plus q charge appears to be concentrated at the center O. That means plus q charge be the charge which is assumed to be concentrated at the center O of the spherical shell. According to Gauss theorem, or according to Gauss theorem, the electric flux crossing through this spherical Gaussian surface is given by the electric flux crossing through the spherical Gaussian surface S, the spherical Gaussian surface under bracket S, is given by phi E equal Q by epsilon 0, where epsilon 0 is the permittivity of vacuum which is surrounding the spherical shell. Permittivity of vacuum which is surrounding the spherical shell. So we get phi E as equal Q by epsilon 0. Here we can assume that plus Q charge be concentrated at the center of this spherical Gaussian surface. In this case, we can denote a number of electric field lines which are crossing normally to the surface of this spherical Gaussian surface. Plus Q charge is uniformly distributed over the surface of this spherical shell, and this plus Q charge appears to be concentrated at the center of this spherical shell. Electric field intensity acts radially outwards, and these lines are also electric field lines which are generated or radiated from plus Q charge. So we denote electric flux or field lines radiated from plus Q charge, and electric flux phi E will be Q by epsilon 0. Or close integration vector E dot vector ds is equal to Q divided by epsilon 0, where Q is the charge on the spherical shell and it is also the charge enclosed by the spherical shell or spherical Gaussian surface, where E is the electric field intensity, that is the electrostatic force experienced by plus 1 charge at the point P, which acts radially outwards. Electric field intensity acts radially outwards, that is away with respect to plus Q charge, which appears to be concentrated at the center O, or close integration E ds cos 0 degree equal Q by epsilon 0, Q divided by epsilon 0, where field intensity at the point P, that is vector E, is parallel to the small elementary area vector ds. Vector E is parallel to vector ds. That's why theta equal to 0 degree. Theta is equal to 0 degree. Here vector E is the electric field intensity which acts radially outwards. Electric field intensity acts radially outwards, and elementary area vector ds also acts radially outwards. That's why vector E is parallel to vector ds, and theta is equal to 0 degree. E close integration ds is equal to Q by epsilon 0, where electric field intensity is constant with respect to the spherical shell, spherical Gaussian surface. In this case, for the Gaussian surface, electric field intensity has a fixed value at every point on this spherical Gaussian surface. That's why electric field intensity is constant, and we can bring electric field intensity outside the integration sign, where electric field intensity vector E has the fixed value at every point on the spherical Gaussian surface, where the electric field intensity has the single fixed value at every point on this spherical Gaussian surface, at every point on the spherical Gaussian surface. Yes. Here we can denote P1. At P1 field intensity is E1, at P field intensity is E. So this field intensity has a single fixed value and field intensity is E constant. That's why you can bring E outside integration sign. Or comma E E 4 pi capital R square equal, in place of charge Q we can write sigma 4 pi capital R square, where sigma is surface charge density of the spherical shell divided by epsilon 0, where close integration ds equal 4 pi capital R square, which is the, not small r square, 4 pi capital R square, which is the area of the spherical Gaussian surface, spherical Gaussian surfaces, and sigma is the surface charge density. Sigma is the surface charge density of the spherical shell. Sigma is the surface charge density of the charged spherical shell. Or comma E equals sigma by epsilon 0. E equals sigma by epsilon 0, where sigma is the surface charge density of the spherical shell. E equals sigma by epsilon 0, which is the electric field intensity, at the point P on the surface of this uniformly charged spherical shell. E equals sigma by epsilon 0, which is the electric field intensity at the point P on the surface of the charged spherical shell. In this case, plus Q charge is uniformly distributed over the surface of the spherical shell. Sigma is the surface charge density, and plus Q charge is appearing to be concentrated at the center O of the spherical shell, and unit positive charge, that means plus 1 charge, is placed at the point P, and this unit positive charge experiences an electrostatic force which is equal to E equals sigma by epsilon 0. That means this is the electric field intensity at the point P on the surface of the spherical shell. This field intensity acts radially outwards, not inwards, and this field intensity acts radially outwards. So hence we get the expression of electric field intensity, which is E equals sigma by epsilon 0.